Okay, I'm starting to record now, so I don't have any issues regarding that. So what we're going to do now is continue where I left off with the slides. Okay, let's start here. Okay, I'm going to share the screen now, people. Look, someone let me know that you can see it okay. Okay, can you see the screen there?
Yes.
Okay, wonderful. Thank you very much. Okay, so let's get moving here.
Yes.
All right, now the key thing, understanding the nature of chemical equations. We've been doing conversions before, and so basically what you need to understand about the nature of these is when you have these things here, essentially that this too can be atoms, it can be molecules, it can be moles, etc. And again, it relates to what's on the other side of the system. So essentially you have makes or reacts to form or whatever else, and it's almost the same as a mathematical equation, okay? And so the different relationships with its atoms, moles, or grams. The key thing is when you start with grams, you got to continue with gram. You change to moles first and then go to grams on the other side. So you have to go through some conversions to see that. Now, balancing chemical equations. First, you write the correct formula for the reactants on the left side and the correct formulas for the products on the right. So if we have something like this, where you have iron plus oxygen goes to ferric or Fe3 iron 3 oxide. You start with that reaction, and then you balance both sides based on what you're doing. So essentially, you go back and forth across. And I do recommend, even on the exam, you use the arrow, use your finger or your pencil, pen, whatever, to do that. Now, the exam today will be using a Scantron form. So I believe Scantrons will be provided for you, so you don't need to buy your own. And basically, you'll use the Scantron to fill in the multiple choice, and then pencils, and please bring a calculator. You will not be allowed to use your cell phone. So keep that in mind as well, okay? So ethane reacts with oxygen to form carbon dioxide and water. You have those things working together there. And essentially, you change the numbers in the front to make the numbers of the atoms of each element on the same of both sides. Don't change the subscripts. So basically, that's changing the compound when you do it. And basically, what I'll do for after the exam this evening, tomorrow morning, I will post a thing for balancing and also for the stoichiometry, some worksheets on both that you can work on over the weekend. And if you have any questions, Monday I will have the time. We can use class as much time as need be to go over any questions you have on the worksheets or whatever else. I just would like you to do the worksheets, and then you'll keep them, and then we'll go over any questions, and I'll just spend the time drawing things and just helping you understand how to do the problems, okay? So basically we'll do that Monday for as much time as we need. So please be open with your questions there. So essentially, you go through the process there, multiplying by the end, and then you have that, okay? Now, you balance those elements that appear in 2 or more products. So the oxygens here is the last step. And I did this before. And then multiply both sides by 2. Now, be sure you have the same number of each type of atom on both sides of the equation. So essentially, you have these working together associated with this structure. So essentially, you count all of them up and make sure they're the same on both sides. Amounts of reactants and products. So the next stage here is to go mass to grams to grams, sorry, grams to moles to moles to grams. So essentially here, this is the reaction. The reaction goes this direction, and you can break off any place along the chain based on the structure of the chemical equation you're dealing with. Okay? So first you write the balanced equation, convert them into moles, use the coefficients in the balanced ones to calculate the moles of the sought quantity, convert the moles of the sought quantity into the desired units. Now methanol burns in air according to the following equations. If 209 grams of methanol are used up in the combustion, what is the mass of the water produced? Okay, so we go to the first stage. Set up the diagram if you like. Set it up just like this. On the page, write it out if you need to. Okay, you first balance the equation. This was already provided for you balanced. So the first thing you do is use the molar mass of the methanol. How would you determine that? Andy, how would you determine the molar mass of the ethanol? Correct, correct. So just add each one together on your paper, okay? The more you use your paper, the better you can practice it, okay? Look at the coefficients in the chemical equation, then the molar mass of the water at the end. You figure out what that is, that's gonna be 18, okay? So you start with 209 grams of methanol. 32 grams of methanol is 1 mole. What cancels? Grams of methanol, very good, okay? Then you go to the next stage. Now, what are you doing when you have the next stage here? What you shifted from the left side of the equation to now you're on the right side. What are you now converting it to now? It went from reactants to what? Products, very good, okay? And now you have moles of water, okay? And then you go use the molar mass of water to change it back to grams again. And that gives you your product, okay? After you cancel out the appropriate things. Now, the units will always help you determine whether you have the right answer or not, okay? So that's the answer there. Now, the next part is limiting reactant. Reactant used up first in the reaction, okay? And essentially, that's the hot dog and bun example I used before. It's very good to keep it in your mind, keep it very simple. Because once you keep it very simple, you can do almost any problem related to these, and essentially you have that. Now, in one process, I believe I sent you the reactions of the thermite reaction. It's really cool to watch. And basically, aluminum is reacted with 601 grams of iron oxide. It's according to that thing, calculate the mass of the aluminum oxide formed. So what would be the first thing you do? This is already balanced for you. So what's the first thing you do? Look for the molar mass of what? Aluminum, yes. The molar mass of aluminum, and someone look at the periodic table, tell me what it is. I can't see it without my glasses. What is it? 26.98. Okay, so this is 26.98 grams, okay, per mole. So always put that in there. Okay, now you're asked, calculate the mass of aluminum oxide formed. Well, then aluminum oxide, you have 2 times 27 plus 60 plus 48. Okay, so that's 54 plus 48 is 102 grams per mole of aluminum oxide. Okay. So basically that's the first part there. Okay, so now what I'm going to do is erase what's on the slide. Okay, so you go grams to the moles of the thing needed, and you go to the grams needed for that. So they're doing it a different way. But what I like to do is do it twice based on how much grams of aluminum you use and how much grams of the other one you use, and then you can practice that to see which one is limiting reactant. Okay, and basically I go for what gives you more product or the other one. So let's do that together. All right, so what we're gonna do first is take the aluminum. We have 124 grams of aluminum. Okay, and it is, what is the number there for the aluminum again? Okay, 27 grams of aluminum per 1 mole of aluminum. Okay, there you go. Now, what's the molar ratio between the aluminum and the other one on the other side? Between the moles of aluminum on one side and the aluminum oxide on the other. You have 2 moles of aluminum gives 1 mole of aluminum oxide. Okay, what cancels? Well, the moles of aluminum cancel. Okay, so now you go to the last step of, then you have this. Okay, 1 mole of aluminum oxide, and then gives how many grams of aluminum oxide? And I'd like you to try it for yourself, please. 1 mole is 102 grams. Okay, so the moles this cancel. So what I'd like you to do now is calculate the numbers there. What are the numbers you get? Someone have a calculator. If you want to do, if hopefully you're working the problem, you virtual people, hopefully you're doing the problem there. So tell me what the number is, please, if whoever gets it first. Yes. Which one? That's 102 grams. I'm sorry for my handwriting. That's the molar mass of aluminum oxide, okay? Did anybody calculate it out? 102 times 124 divided by 27 and 2, divided by 54. $124 times 102, and to divide that by 54. What does that number equal? 234.22, right? 234.22 grams. Okay, so write that down, please. Okay, now let's do it with the other one. 601 grams of iron oxide, 601 grams of iron oxide, Fe2O3. You got to get the molar mass of iron oxide. So look on the periodic table, what is iron over there? 55.85. So essentially we have iron oxide 55.85 times 2, and that's 111.7 grams, okay? Plus 48. So that totals to be 149.7 grams, okay? So you go this way now, 149.7 grams of iron oxide is 1 mole of iron oxide, sorry. And what's the mole ratio between that and aluminum oxide? It's 1 to 1. So you have 1 mole of iron oxide, and I encourage you to try it for yourself. There is 1 mole of aluminum oxide. Okay, and then you have again 1 mole of aluminum oxide is 102 grams. So pardon my handwriting again, with this, hopefully you're doing it on your paper. Okay, so you see how I did it twice. So what is the number now? This is 601 times 102 divided by 149.7. 5. Okay, what is that number going to be? $601 times 102 divided by 149.7. 409.50. Okay, so which gives you less product? The aluminum. So which is the limiting reactant? The aluminum is, okay? So essentially you went through the same process twice. Now I'm going to delete what's on the slide and show you how the book does it with this slide, which is a different way of doing it. Whichever way you can understand the better, use it, okay? So basically what I'm going to do now is erase all the ink on the slide, and then we'll show you what the book does with this here. Okay. So you start with the grams of aluminum, you convert it to moles there. You know 2 moles aluminum gives 1 mole of iron oxide there. The 1 mole of iron oxide is 160 grams, okay? So they rounded it. So these cancel. And that's 367 grams of iron oxide. So what does that tell you first? When you do it that way, what does that tell you immediately? It only requires 367 grams. So what is the limiting reactant? The aluminum. It would have to require the whole amount or more of it, okay? So this way is the way to say that the aluminum is the one, okay? But it doesn't really answer the question. I honestly get confused when I did it that way too. I always found it easier just to do both and see what gives you less product, okay? So whichever way works for you, the better, but we all don't think alike. So you start with 124 grams of aluminum, you need 367 grams of iron oxide. You have too much, so that means the aluminum is there. So aluminum is the limiting reactant. That wasn't the question that was being asked, was it? You were asked the mass of aluminum oxide formed. So basically what I'd like you to do is try and do it both ways. You do it first with this one. You do it first with this, go through the process, and then do it with that one and see which gives you less product. That answers the question. It also answers which one is the limiting reactant. And I'm going to, in the exercises I'm going to pass out to you, I essentially will be an old quiz I used at another university. I'm going to go through that process and make sure you understand how the process works regarding that. Okay, so I want you to try and do it for yourself, going through the process using a simple process first and then the other one. So basically it's a very straightforward process, okay? Now you use the limiting reactant to calculate the amount of product. And remember, they did this already. They did this already with it. And essentially this is, again, this is what I did before, okay? Canceling out the values. And then we get to 234 grams of product we got, okay? And then we found the other one gave you more. At this point, all the aluminum is things, and so your answer is 234 grams. But I find the other way less confusing, even though it's a little bit more work, because once you practice it, you'll get the hang of it better, okay? Now the reaction yield has to do with what is expected. The theoretical yield is the amount of product that would result if all the limiting reactant was reacted, okay? So the theoretical yield in this case is 234 grams. Okay, so the theoretical yield with that, but say you got 200 grams at your end, 200 grams of aluminum oxide, and you're expecting 234 grams of aluminum oxide. The reaction yield will be 200 out of 234. Why could that possibly happen? Why could that possibly happen? Any ideas? Well, you could spill something. Usually it's spillage, okay? Or just calculations at the end. So the actual yield is the amount of product actually obtained from it. So that could be actual based on spillage, or it can be based on other things related to this. So actual yield is the amount of product actually obtained. So the percent yield is the actual divided by a theoretical yield times 100. Now, chemistry in action, chemical fertilizers, there's a couple examples here, and essentially making fluoroapatite and such like that. And I had the pleasure of teaching at Plant City campus of Hillsborough Community College. There was a fertilizer plant there that essentially its raw materials were phosphate rock that they dug out of the place on Pacific Islands and in Florida also. They took phosphate rock, they took sulfur that they burned and went through the process to make diammonium phosphate fertilizer. And it's really quite cool there to see that. Okay, so I'm gonna, essentially this slide thing is now finished, okay? So now I'm gonna go to the other one and go to the other slide so you can see how the other book uses it, just to refresh where we're at with this. Okay. Now, what's weird about this is it's not, this one is not very helpful because he doesn't really go through the steps, but I'm going to use it because this is our textbook. So if it's helpful for you to do that, what I'm going to do is write on the slide and kind of highlight what I just talked about in the other book, okay? And the best thing you could do now for the weekend after the exam this afternoon is to work the problems in chapter 3 in your textbook and go to Hein. Okay, go to Hein and essentially Hein chapters 7 and 8 primarily, and that spreads it out more into little pieces that some of you may need to work with. Okay, so here, how many grams of sodium hydroxide are used to react, needed to react with 25 grams of chlorine? Okay, so basically, essentially, this makes it more complicated, but what is the first thing you need to do there? How many grams of sodium hydroxide are needed to react with the chlorine? What's the first thing you have to do there based on what we did before? Yes, very good. Convert the chlorine, 25 grams of chlorine to moles. So let's do that. 25 grams of chlorine. So what's the molar mass of chlorine? So look on there, what is it? Okay, so that's 70.9 grams of chlorine, okay? Per 1 mole of chlorine. So grams of chlorine now cancel. How many grams of sodium oxide? What is the mole ratio between both of them? In the thing, it's given there. How many moles of chlorine with 2 moles of that? So 1 mole of chlorine requires 2 moles of sodium hydroxide, correct? Does everybody see that? I got it from this and that. Okay? So essentially moles of chlorine cancel. Now what's the next part? Converting into grams. So look at sodium, it's 23 plus 17 is 40. So now you have 1 mole of sodium hydroxide, again, is 40 grams of sodium hydroxide. The moles cancel, and now all you do is the math. Now, with this thing, did they ever go to the product side? No, it's based on just the reactants. But on my exam, I'm basically always going to go to reactants because I don't know anybody that would try and figure out exactly how many grams of the other stuff to use. Practically, it's not very useful there because normally the things are mixed. This reaction is done in air. They provide an excess of both of them, an excess of one that's easy, and then figure it out and then figure out what the yield is. But it's useful for you to at least understand what's going on regarding that. So I recommend you kind of go through this yourself when you're doing your studying just so you can see the difference. But this is essentially what I did before in my bad handwriting. Yes?
You said reaction yield?
Yeah, the reaction yield is how much you get in when you do it.
Yes.
The theoretical yield will be different.
Is that going to be on the test?
Reaction, yeah, actual yield versus things. And it usually has to do with the theoretical yield is if everything works perfectly. The reaction yield will be the amount of product you get that's pure. Yes.
Okay.
No, this is not on the test today. This is on the test for chapters 3 and 4. Essentially this week we're finishing chapter 3. So essentially the worksheets you work on, and we'll have a quiz on chapter 3 next week, perhaps. Yeah, I will have a quiz on chapter 3 next week and then continue with chapter 4. So there will be a quiz, but it'll be in class probably on Wednesday. And then we'll continue with chapter 4, and then we'll have another one for 4 and then have our next exam. So that'll go relatively quickly. But again, here we have the grams of this cancel, the moles of chlorine cancel, the moles of sodium hydroxide cancel. Now you have 28.2 grams of things, just like I had in my bad handwriting before. Yields, the actual yield is the actual amount actually formed in the reaction. The amount predicted by calculations there. So you have the actual yield divided by theoretical yield is the percent yield. And the limiting reactant is a reactant that's present in the limiting amount. That's essentially when you have 4 hot dogs and 2 buns, the buns are the limiting reactant. The excess is the other one, and it's left over. Remember, when you have a chemical reaction and one material is, you have too much of it, when one material, you have too much of it, basically the key thing is regarding that, when there's too much of one thing, will it react with anything in the system if you've already reacted all the other material? No, it'll just sit there, okay? Once the reaction is finished, it will just sit there. So essentially, excess reactant just sits there and needs to be separated. Okay, now here, at high temperature, reactions with limiting reactant, ethylene oxide reacts with water to form ethylene glycol. Because water is so cheap, it's used in excess there. So essentially, they can get all the material conceived. Now let's look at this thing. If 3 moles of ethylene oxide are reacted with 5 moles of water, which one is limiting and which one is presence and excess? Okay. So the first thing you have to do is balance the equation. Okay, and if you look at the equation, it's already balanced there. What is the mole ratio between the ethylene oxide, which is this one, and the water? What's the mole ratio there? What? No. In the equation. It's 1 mole and then 1 mole, correct? You see that? There's 1 mole and 1 mole. Which one is in excess? 3 moles of aluminum ethylene oxide or 5 moles of water? Which one is too much? The water is too much, okay? Because it would be 3 to 3. Okay, the 3 to 3 would go together. So this would essentially be 3 would mean you have 3 moles of water. So what is excess? The water is excess. You have 5 of it. Does it react with anything? No, it just sits there. Okay? The reactant that's limiting is the ethylene oxide. Okay? So you look at the 2 different things related to it.
How did you do that without creating a process?
Well, you just look at the mole ratio. Let me go over here so you can see this. This is a 1 and this is a 1, correct? You're doing 3 and 5. So if you have 3, if it's 1 to 1, if you have 3 moles of the ethylene oxide, how much water would be required? 3 also, but you have 5. Okay, so that's essentially how it works. Okay. Okay, and then they give you a little diagram there with the 2 extra unreacted material. Now, lithium oxide is used in the space shuttle to remove water from the air supply according to the following equation. If 80 grams of water is to be removed, and you have 65 grams of lithium oxide available, which reactant is limiting? And again, I'd recommend you do it with both ones. Okay? You start with the 80 grams of water, you convert that to what? Moles, yes. Start with this, go to moles. So essentially you start with 80 grams of water, and then you have 18 grams of water is 1 mole, okay, of water. And then how many, and then essentially the next part is you go to the amount of sorry, this is water again. 1 mole of water, okay, gives 2 moles of lithium oxide, lithium hydroxide. Pardon my handwriting again. Okay, and so the moles of water cancel, the grams of water cancel, and now you have the moles there, and then you can convert that to grams. 1 mole of lithium oxide, hydroxide is, you look on the thing there, it is 7 plus 17, so that's 24 grams of lithium oxide. Do the math, figure out how much product you get. And then essentially the other one, you start with 65 grams of lithium oxide to get it, and then go the same way. So essentially you go all the way over to the other side. Okay, now what we'll do now is use the slide to look at it. The amount of water that we react with 65 grams of lithium oxide. So essentially we start with this. 65 grams there, these cancel, 2.17 moles there. The amount of water given is 4.4 moles. So the lithium oxide is limiting there. Okay, so essentially that tells you first thing, the lithium oxide is limiting. Then how many grams of excess will remain? Well, you can also look at this also when you have this associated with this, 2.17 moles of water, and you have 4.4 moles of water. Lithium oxide is limiting. How many grams of excess water remain? So you take that number from before, you convert it to there. This is how much is consumed. And you look at how much you have initial, and then the amount consumed, and that is how much water you have left over. And unfortunately, this slide doesn't really go through that process, but I'd like you to try it for yourself at home. Okay? And so basically how many grams are produced, that's the last part there, and you get the 104 grams of lithium hydroxide. Percent composition and empirical formula, I already did that in the previous, with the previous slides. Okay, determining that with this. Okay, so we're essentially done that. So, oh, a second now. Okay, now what I'm going to do lastly now is just show you briefly the other one. Okay, I'm going to go to chapter 7 here just to show you this. Okay, this is percent composition for chapter 7. You can kind of see how that works there. And let me close this. I don't want to close it. I want to go show the other one. We have about 5 minutes left, so I want to show you how this works. Okay, I'm going to share the screen again, folks. Okay, can you see the PowerPoint there? Okay.
Yes.
Okay, wonderful. Okay, what I'm going to do now is go through the slides. I'm not going to write on much, but this is chapter 8 in Hein. The chapter 7 is more basic stuff for the material we covered a little earlier. So to summarize the reaction, display the substances that are reacting. There, the chemical equation always involves change. They rearrange. You have reactants and products. So for example, this one here, you have aluminum reacts with iron oxide to form iron and aluminum oxide. That's the thermal reaction there. You have that, the reactants and products on both sides. So this is very basic stuff. So if it's helpful for you to use the basic stuff first, to go through this first, by all means do it. Then go to the other ones for our course. Okay, this will give you any background that you need to do this. The coefficients, essentially you want to balance them. So you have to balance them related to putting the coefficients in front there. And heat is the thing with there. You have heat associated with it. Solids and liquids are the material there. And chemical reactions, atoms are neither created or destroyed. And chemical symbols there, essentially it goes through all the different details we kind of went over with them. Writing balancing equations there, you identify that, balance it, and notice it goes through multiple steps to do it. You see it? See how he's following more there? So these will be available for you to do that, and then balance back forth there to go that, going back and forth across. So essentially we did this before with our slides here. Essentially, you have 2 oxygens over here. You got to put a 2 in front, and then this requires a 2 there to balance it. And basically, we just keep going there. Balance the equation there, balancing, practice questions going that way. And I'm going quickly because I want to just show you what's there. But there's some more examples there associated with it. And this is in multiple steps. Types of things, and that's covered later. Okay. So basically we'll talk about types of reactions later. But what I want to do now is go further. Oh, okay, that's different. And chapter 9 is calculations with this. Essentially, we have number of moles associated with this, mole ratios. Essentially, this is what I was talking about before with that. So basically, if you look at the different steps there, calculate grams, this goes, so gives some more examples there. So this is chapter 7 through 9 in Hein. So I highly recommend you use them if you need to. If you don't, if you understand this, that'll be fine. Are there any questions for those of you distance? Okay, thank you very much. I'll see you this evening at either 7 o'clock or 8 o'clock. Thank you. Have a good day. Yes.